Before starting, I'd like to express my gratitude to my colleagues and their contributions, including Hassanzadeh from Chinese University of Mining and Technology, from China, Hamid Khoshtas from Zeland University, Iran, and Peshamistov Kowalczyk from NTNU. Today I'm going to give the presentation on recent developments in generating, detecting, and observing ultrafine bubbles, so-called nanobubbles, tiny bubbles, and micron size bubbles, as well as their applications into mineral processing and more specifically to froth flotation. It has been more than 2 decades that scientists use this ultrafine bubble technology in order to adapt it for to different applications, including mining and mineral processing. But looking at other applications, we see more development so far, including cleaning and sterilization, beverage industry, food and agriculture, drug delivery, and medical science, as well as wastewater treatment. Just giving some examples from these applications. In case of a beverage industry, for example, while we are going out of the city in order to have a fresh air and breathing in, we get a good feeling when the level of the oxygen is higher compared to the inside of the city. The same is with the beverage industry. When the amount of oxygen or dissolved oxygen inside the liquid and the bottle of water is higher, it gives a better taste as well as it is healthier. When it comes to the food and agriculture industry, as you see from top right hand side, fish is treated with nanobubbles. They grow faster, their survival rate is higher, and the meat taste is better. In terms of broccolis treated by tap water and oxygen nanobubble water, as you see, there is a growth and they have higher heights when they were supplied by ultrafine bubbles. Scientists already proved and applied ultrafine bubbles in order to open up some blood barriers inside some local places of human bodies and deliver the drugs quite effectively. In case of the mineral processing and wastewater treatments, we can decrease the cost of water supplying, as well as increasing the, let's say, metallurgical responses, more specifically recovery. By looking at the historical data, it has been quite clear to everyone that there has been a long-standing and intensive argument between the scientists so far, whether because a group of the scientists, they didn't believe the nanobubbles, and the other group accepted this, and they acknowledged that it's possible to create nanobubbles, and those bubbles, whether bulk or surface nanobubbles, are stable in the bulk solution or on the surface of the solids. By just scanning the literature data, it's quite clear that from the middle of the 19th century, scientists and engineers and researchers, they focused more on bulk nanobubbles, but by passing time from the year 2000 with emerging atomic force microscopy and other techniques in order to tangibly sense and physically observe the nanobubbles, scientists started to believe that, okay, it's possible to detect and observe and track these bubbles, and they believe the concept. Nowadays, what we see is more applications to this concept and more developed technologies in different areas. I've seen in some literature data or scientific publications that scientists and researchers, they show such a cloudy and milky water and refer it to the nanobubbles, but this is wrong. Mostly this kind of bubble this kind of water, what we can see the bubbles and these milky water, actually it contains ultrafine bubbles. If there are nanobubbles into the system, so it's impossible to see with the naked eye. Before applying nanobubbles into the system, into any system, we need to understand them profoundly and deeply. You see here a picture showing the classification based on the size of the bubbles and the behavior of these bubbles, as well as the mass transfer and retention time. It is interesting to mention that bubbles finer than 1 micron have been considered as ultrafine bubbles. But so far, to the best of my knowledge, there is no standard definition for that. But it has been commonly accepted and acknowledged that bubbles smaller than 1 micron can be considered as ultrafine bubble or a nanobubble. From 1 micron to tens of microns or even 100 micron can be called as a submicron bubble. And from 100 or 50 micron to 900 or something is considered as a micro bubble, and over than that, above than that, we call them a macro bubble, which is actually the bubble size we deal with in conventional flotation cells, from this area to this area. So what happens actually is when we deal with big bubbles, millimeter size micro bubbles, or even a part of this range, bubbles they rise very fast. Their velocity is high, around 10 to 30 centimeter per second, depending on the medium and the reagents into the system, as well as the generation technique. These bubbles, since they move very fast to the surface and will be collapsed on the surface, they have a poor mass transfer, and their retention time is very low. However, by decreasing the size, the movement changes. They go to the right and left. This zigzag behavior allows them in order to have more interactions with particles, if we have in the system, which is very common in froth flotation. This allows them to interact with the particles, and the particle bubble collision attachment, the attachment can be taking place more effectively. In addition to that, their retention time is higher. They also will be collapsed inside the bulk. By collapsing, they can also remove some slime coatings from the surface of the particles and clean the surface of the particles, or even the passivation layers from the target minerals. When we decrease the size further and further, we will come up with Brownian movements of the bubbles, and in the unit of the volume of the cell, we will have a very dense, very high number of the bubbles, as well as the surface area will be increased. So size will be decreased, the movements will go toward Brownian movements, longevity will be high, bubbles will stay longer, surface area increases, surface charge highly negatively charged, stability, they will be more stable, and in some reports you can come across with numbers like days. Contact angle will increase, the dissolved oxygen level also will increase dramatically, and it's very effective for cleaning. Just some examples in case of froth flotation. What you see here in the conventional flotation cells, we have millimeter macro bubbles, or hundreds of the micron size bubbles. Their surface area is very low. However, in case of pneumatic flotation cells, such as a Jameson, ImhoFloat, or reflux flotation cell, we have a very large number of the bubbles, which provide more surface area. This is very beneficial for particle bubble encounter, collision efficiency, and improving the recoverability of fine, also coarse particles. They reduce the collector's consumption because they act like a secondary collector. They have also a cleaning effect, removing the passivation layers and also slime coatings from the surface of the target minerals and letting them to interact with the reagents, mostly collector, and let them to have higher absorption rate and densities. Besides that, they create also hydroxyl and hydronium radicals. This changes the solution chemistry. In case of the contact angle, so as you see here, a picture represents the picture of the quartz surface in the absence and the presence of the contact of ultrafine bubbles. As you see here, the contact angle is around 80, which substantially increases to 45 while being treated with ultrafine bubbles. In terms of the bulk surface nanobubbles, we have these bubbles will interact with the surface of the particles and make them negatively charged because of the nature of themselves. They are highly negatively charged and they are more stable in alkaline condition. Very quickly, so far most of the research activities have been conducted on monominerals, as you see here, but recently researchers focused more on bulk material, which is the actual condition in froth flotation. And as you see here, always we have an improvement on recovery. In case of apatite 8, around 9%, phosphate 35%, and hematite 16%. In case of the grade, we have seen some reports showing the negative, even no effect on the grade, and in some cases we have seen a positive effect on the grade. This is very sensitive to the mineralogy of the bulk material. The mechanisms that we have in case of interacting these ultrafine particles, bubbles with the particles, for fine and coarse particles are different. In case of the fine particles, we have a coating of the nanobubbles on the surface of the fine particles. They attach to the conventional bubble sizes. When it comes to coarse particles, because these fine bubbles are ultra-fine bubbles, they cannot lift the coarse particles to the surface. They need conventional size bubbles in order to help them for lifting the particles to the top, to the froth soil. There are different techniques in order to generate and produce nanobubbles, as you see here, but mostly researchers have focused on hydrodynamic cavitation and power ultrasound, as I'm going to describe these techniques a bit in details. In case of the cavitation mechanism, what you see, it's also applied. It has been applied for froth flotation, and it can be used also for hydrometallurgical purposes. What we have, a typical venturi tube, the flow comes to this area, and we have a straw. Then the negatively created pressure allows the bubbles to be shrinked, and we have a large number of ultrafine bubbles as a product. It should be also noted that pH, temperature, pressure, airflow rate, froth type, dosage, water properties are also very effective factors. It depends on the system, and we can control the ultrafine bubble sizes based on these parameters. In case of the hydrometallurgy and specifically gold leaching, it's possible to add nanobubbles in order to increase the dissolved oxygen level. By this, it's possible to reduce the cyanide consumption, which is very important from the environment. This follows Henry's law. Based on the temperature, by increasing the temperature, we have a reduction in dissolved oxygen level, and also increasing the pressure increases the level of DO. But it should be also noticed that we have to consider the radicals like hydroxyl and hydronium created by nanobubbles into the system, because they will play some roles on chemistry of the system. With respect to the ultrasonic treatment and creation of the ultrafine by ultrasonication, 3 factors are very important: time, power, and frequency. As you see here, at low frequencies between 20 to 50 kilohertz, we have transient bubbles here, as you see. then these transient bubbles, they are not stable, but they can remove the slime coating from the surface of the particles. By increasing frequency to the range of 200 to 1000, then it's possible to make a stable cavitation effect, and this allows to aggregate particles and float them to the surface. We did an investigation together with a PhD student from Morocco University, Poland. As you see here, two graphs. This is the graph after creating nanobubbles by ultrasonication in different power levels, 0, 20, and 60. Here, absence of nanobubbles, and we tried to detect the nanobubbles by two methods, including the laser particle size analysis and dynamic light scattering. As you see, with this technique, it's impossible. With LPSA, it's impossible to detect nanobubbles, but here we could detect nanobubbles in this range. As you see, this black line, continuous line, is in the absence of ultrasonication, and 20 and 60 watts, as you see, the red line and blue line. It has been already reported that if we want to detect nanobubbles, we have to use DLS, but mostly I've seen in the literature that people use LPSA, which provides some uncertainties. With respect to the number of the publication, as you see, it increases, showing that researchers pay attention to this subject more than before. And in terms of improvements on metallurgical responses, as you see, for a wide variety of the particles, we have an improvement from, let's say, 5 to around 40% on recovery of different minerals. To sum up, we can say that surface nanobubbles enhance the contact angle, act like a secondary collector, and reduce surfactants, mostly collectors' consumption. They are effective for both fine and coarse particle sizes and act with different mechanisms. Main improvements have been addressed on the flotation recovery and kinetics rate. The selectivity and the grade they are still ongoing in the literature. More experimental data is required for bulk ores to ensure its pilot and industrial scale development. Thank you very much for your attention.